Hi everyone, we're going to go over lesson 4.6, day 2, finding the equation from the graph of an exponential function. You will need the handout that you got from the last lesson on exponential functions transformations. We will be going over the last page. Before we look at how to find the equation from the graph of an exponential function, we may want to review the basic types of exponential functions from 2 days ago. So there are two types of exponential functions. One rises from left to right. We call this an exponential growth. We know that we have an exponential growth when the base function y equals to b to the power of x, your b value is greater than 1. And we have a second type of exponential function. It's called the exponential decay. So this happens when the b value in y equals to b to the power of x is between 0 and 1. Notice there are two common features on these two graphs. Whether you have an exponential growth or decay, you should know that their horizontal asymptote is the x-axis, which has the equation of y equals to 0. And also both of these graphs passes through the point 1. So when I give you a graph and I'm looking for the vertical stretch, it's very easy to tell what the vertical stretch is by simply comparing the distance between the y-intercept and the horizontal asymptote. Anything other than 1 means that the function has been stretched vertically. And of course, we're simply assuming that there are no shifting or anything that's happening as yet. Okay. So now let's go back to the handout and we will go over a few different examples. Because of the nature of the exponential function, we can actually simplify the parts where you have b to the power of x, and using exponent laws, you can actually recombine those horizontal stretches or shifting back into and distribute those numbers into the vertical stretch and the vertical shift. As a result, we are not going to look at any types of horizontal transformations when we are examining these graphs, just to make things a little more straightforward. The form of equation that we're going to write for each one of these graphs will be y equals to a times b to the power of x plus c. So as you can see, a is multiplied to b to the power of x. This is a vertical stretch. And then x is just simply an x. So that means there is no horizontal reflection, compression of stretches, or shifting. But plus c is added at the end of the function to show that show any kind of vertical translations. So we're going to start with the very first graph. The first thing that you can tell from each of these graphs should be the vertical translation. Because if the graph's horizontal asymptote is not the x-axis, it will tell you that the position of the graph has been moved. Let's take a look at the first graph. Well, obviously, the horizontal asymptote is still on the x-axis, so it tells me that the c value will be 0. There's no vertical shift. The next thing that we can look for is any vertical stretches. Remember, for all exponential growth or decay functions, the base graph will have a y-intercept at 1. But on this particular graph, the y-intercept is 2. Or we can say that f of 0 is 2. So we said that the distance between the horizontal asymptote and the y-intercept gives you the a value. Specifically, it can be found by f of 0 minus c. So a in this case would equal to 2. So we have already found a and c. Our equation now looks something like y equals 2 times b to the power of x plus 0. So you can skip that part. The last thing that we need to find out then will be the value of b. In this case, we can use any point on this function to help us to find the value of b. When you're looking for these points, make sure they're very easy to read. So you wouldn't choose anything like somewhere on the graph that is hard to tell. You have to do a lot of estimation. Also, another tip is to pick small x values, whether it's like a small positive or small negative values, because that will make your simplification a lot easier. Well, fortunately, if I slide along this function, when x is equal to 1, y is equal to 6. So this is an exact point. So that means I can use the point 1, 6 in my temporary equation. You substitute 6 into y and 1 into x. So now you have 6 equals to 2 times b to the power of 1. Dividing both sides of the equation by 2, well, b to the power of 1 is b, so you have b equals to 3. So now you have found a, b, and c. You summarize it by writing the equation as y equals 2 times 3 to the power of x. Question B. So on this graph, the first step, we can locate the horizontal asymptote. This time it's at -7. It automatically tells me that c is -7. Then the y-intercept, f of 0. It has a value of -6. With these two pieces of information, I can now find the value of a, vertical stretch, which is f of 0, -6, minus the c value, -7. It works out to 1. And then you also need a third point or second point on the graph to find b. F of 1 is equal to 0. So this is convenient. We have 1, 0 on this exponential function. So putting this all together, my temporary equation is y equals 1 is a times b to the power of x minus 7 because that's c. Plug in the numbers 0 into y and 1 into x using the point. When you solve for b, you get b equals to 7. So that means the equation is y equals to 7 to the power of x minus 7. Question C. So this time we do see a slightly different exponential function. Well, in the back of our mind, we know that both exponential decay and growth, they stay above the horizontal asymptote. But this graph is below the horizontal asymptote, so there must be some kind of a reflection. The horizontal asymptote C is 0. Y-intercept f of 0 is -5. So the a value is -5 minus 0, which is -5. This makes sense because we said that, well, that must be a vertical reflection, so a is negative. You need to find another point to figure out b. In the last two examples, we use f of 1, but on this graph, if I make this a little bigger, well, f of 1 is not exactly -3. So it may not be the best point to use. But we can see that the point -1, -10 is exact. So in this case, I can use the point -1, -10 to find b. So substituting all the given numbers, y is equal to -5 from a times b to the power of x plus c, which is 0. So we have this form. substitute negative 10 as y, negative 1 as x. Divide both sides of the equation by negative 5. And then I have to find the value of b. We know that b to the power of negative 1 is 1 over b. So solving for b, we may want to multiply b to the other side first, and then dividing both sides by 2 to get b equals to 1/2. So if you imagine you're reflecting this given graph back upward, you see an exponential decay, which matches with the idea of a 1/2, a number base that is between 0 and 1. So your final equation is y equals to negative 5 times 1/2 to the power of x. And here is our last example. So we're following the exact same steps. Okay? Horizontal asymptote is 3. So c is 3, is shifted up. F of 0 is 1. While this y-intercept is below the horizontal asymptote, so we expect a value that is negative. So the a value will be f of 0, which is 1, minus the c value, which is 3, and a is negative 2. A point that is convenient to read on the graph is 1 and negative 1. So using all these information, we have a temporary equation, y equals negative 2 times b to the power of x plus 3. Substitute the point, 1 and negative 1. So make sure negative 1 is the y value, 1 is the x value. Subtract 3 from both sides of the equation. I get negative 4 equals negative 2b. Divide both sides by negative 2. b is 2. In other words, I have the equation of y equals to negative 2 times 2 to the power of x plus 3. There are many different forms of this equation, and because the x applies to just a 2 here, you can also put it outside of the equation.